Greetings everyone! Today we're going to talk about simple harmonic motion, also known as periodic motion, also known as oscillations. This covers pendulums and masses on springs going back and forth. Really anything that goes back and forth in a periodic way. First, though, you need to watch some of the videos that I put in the description. So go to the description on this video, check out the links in that description. It is very important that you watch those videos first because that will kind of explain exactly what I mean when I talk about simple harmonic motion and periodic motion and all that. So definitely watch those videos before you continue on, and after you watch those videos, I will see you. I hope everyone has watched the videos that I linked in the description because that will be very important to understanding what is going on here. Simple harmonic motion is also known as periodic motion. It's also known as oscillations. Anything going back and forth in a certain period, oscillating in that period, can be described with simple harmonic motion. That's approximately true. The examples that we're going to talk about are all contiguous with each other in this way. But if we have a mass here that is attached via a spring to a table, the side of a table or something like that, and it's on a frictionless surface, if you take that mass and you pull it that way and release it, the mass will oscillate back and forth forever if there's no friction anywhere in this system. We talked about this when we talked about springs originally. So go back to that lecture on springs in the files section and refresh yourself about how this works. The videos that I linked also talk about how this works. But if the mass is pushed this way, then the spring wants to push back that way, and it tends to push the mass back that way. If it gets stretched all the way out that way, the spring wants to pull it back in, and so it starts coming back in. So refresh yourself about that. Pendulum, kind of the same. As the pendulum swings back and forth like that, gravity is wanting to pull it down at any point, and when it's over here, pulling it down is tending to pull it kind of this way. There's a component that is this way when it's pulling down, and when it's over here, it's still being pulled down, and there's a component back towards the center when it's over there. So because of that, the pendulum will just swing back and forth forever. That is simple harmonic motion, or periodic motion, or oscillations. Can we describe this kind of motion mathematically? Well, this wouldn't be much of a physics class if we couldn't describe things mathematically. So here's some equations. The omega of something is equal to 2 pi times f, that's going to be frequency, which is equal to 2 pi over t, that's going to be period. Well, what do any of those mean, actually? Omega is the angular velocity, which we've already seen, radians per second. We are actually going to call omega a slightly different word. Instead of angular velocity, we're going to call it angular frequency instead. Omega is a measure of how quickly something moves back and forth. Something that's moving back and forth very fast is going to have a very large angular frequency, but something moving back and forth much slower is going to have a much lower angular frequency. Watch those videos that I linked and you'll see the relationship between angular velocity, which is more of a circle kind of thing, versus angular frequency, which is a back and forth kind of thing. If you've watched those videos, you know what I'm talking about. The relationship between angular velocity going around in a circle and angular frequency going back and forth. Watch the videos. Okay. F is frequency. Frequency has units of 1 over seconds or hertz. You see here, radians per second. The angular frequency is also radians per second. Same units, of course. Here we don't have radians up there. I said earlier that radians is kind of a fictitious unit that you can just throw in there whenever you want. That's approximately true. but here we don't have that radians, nor should we. Frequency is how many times you would go around in 1 second. How many times you'd make a full revolution per second if it's circular. Frequency, the circular version is revolutions per second. Complete revolutions, complete rotations per second. Angular velocity was how many radians you go through per second. So there's a difference in 2 pi between them, which you can see here. Omega is equal to 2 pi times the frequency. If you go around a circle once per second, then you're going around 2 pi radians per second. So that's consistent with what we've already done. We're just turning that from circular stuff to simple harmonic motion or periodic motion or oscillations. A lot of the engineers out there know that 1/seconds is the equivalent of hertz. Both of these are just fine. Hertz, how many cycles per second you have, full cycles per second. And then t is the period, which is in seconds. Frequency is how many times per second something moves back and forth. So if it goes back and forth 5 times per second, then the frequency is 5 hertz. The period then would be 0.2 seconds. If it goes around 5 times in 1 second, then that means that one rotation, one full back and forth, should only take 0.2 seconds. That's the relationship between frequency and period. 5 hertz, or 5 revolutions per second, that's going to be the equivalent of 0.2 seconds for the period. On the opposite end of the spectrum, if something takes 10 seconds to go back and forth, then its period would be 10 seconds. Its frequency would be 1/10 of a hertz, or 0.1 hertz, or 0.1 per second, 0.1 rotations, revolutions per second. But this is a back and forth thing, not necessarily a circular thing. So watch those videos. Well, what can we do with those omegas and frequencies and periods and all that? If we have a system, a simple harmonic oscillator, something in simple harmonic motion, a pendulum swinging back and forth, or a mass on a spring moving back and forth, then we can convert the frequency or the period into the angular frequency omega, and then we can get these kinematics equations for an object in simple harmonic motion or periodic motion. The position of an object as a function of time in a simple harmonic motion is equal to the amplitude of the motion. If you've got a pendulum going back and forth like this, then the amplitude is measured from the center of the oscillation to the maximum. If you can find the center to the maximum, that is the amplitude of the oscillation. If we have a mass on a spring, say that there's a spring there attached to my hand, I guess, and let me make this a little bit darker so that you can see it. You've got some mass here, and it can go back and forth and back and forth. You take the distance from the equilibrium position to the farthest position that it gets stretched out. That is your amplitude in that case. So amplitude is measured generally in meters, and that goes there. So if you see an equation that has some number times a cosine times stuff, and we'll talk about that stuff, the number in front of the cosine is going to be the amplitude of your oscillation. You need to learn to interpret equations like that. If you just see some equation with some numbers in there, then you need to be able to interpret what those numbers mean. And in this case, the thing in front of the cosine is the amplitude of the oscillation. Okay, well then we have a cosine. And we've got all this in the cosine term. What is any of this? Well, that's omega. That is your angular velocity in radians per second, as we talked about, times time. Well, this is x as a function of time. So you can plug in a time in there, and you should be able to find the position of an object at any given time. If you plug in 0 seconds or 1 second or 2 seconds or 48 years or whatever into this, then it's giving you the position at that time. All you need to do is plug in that time there and plug in all the other numbers that you know, and you can get the position out of that. T, time since it started oscillating. Phi is that symbol. That is the phase angle, which is the initial position. You might not start all the way over to one side or all the way over to the other side using this example again. You might not start in the middle. You might start with it already compressed, already stretched out, or something like that, or halfway between 0 and stretched out or something. And so that phi will tell you that phase angle, that initial position as an angle in the oscillation. So watch those videos that I have in the description, and that angle stuff will make sense. And then x of t is the position at some time t. Here is kind of a simple example of what I'm talking about with being able to interpret an equation. If you just saw an equation like this without any context, it would be kind of hard to discern what it was talking about. But I hope that after today's video, you'd be able to look at something like that and begin to think of it as, oh, well, it's really just some sort of kinematics equation for simple harmonic motion. We've got the position at a time of 3.4 seconds. So whatever is going on, it's at a time of 3.4 seconds, is equal to 9.7. Well, that must be the amplitude of this oscillation. That's the amplitude of the oscillation right there. Time, so it must go from, if it's a pendulum swinging back and forth like that, then the distance from there to the maximum distance should be 9.7 meters. That's the amplitude. So there to there, 9.7 meters. The 0 position, the downward position to either of the maxima should be 9.7 meters. That's the meaning of that. Times the cosine of 0.88, well, that has to be omega, the angular velocity. That's a measure of how quickly it's going back and forth, either very fast or much slower. Times t. What are we going to plug in for t? Yeah, we have to plug in that. This is the t that we have to plug in, so we'd better be plugging that in for t right there. Minus 0.01, well, that's the phase angle, that's the initial position. So it was actually very close to whatever the 0 is initially. So get, a little bit of practice just learning how to interpret these kinds of equations. If you're just, randomly given that equation, know what you can do with it using this kind of kinematics of simple harmonic motion right there, how to interpret all these numbers. Is there anything else that we can do with an equation like this? With the position as a function of time is equal to some equation? Can we find the velocity as a function of time this way? Yes, we can. Go ahead and try to figure out the velocity function given this initial function. What is the velocity of this pendulum or this simple harmonic oscillator or this mass on a spring as it goes back and forth? Find the velocity of that as a function of time using calculus, using your calculus knowledge. All right, did you get this? That the velocity as a function of time is going to be negative times a times omega times the sine of that interior garbage? I hope so. That's some good calculus right there to look at. And what about the acceleration? Can you find the acceleration? Is that the acceleration that you found? Yeah, so negative amplitude times omega squared times the cosine again of omega t plus phi again. Well, we can do quite a bit with this kind of kinematics, and we're going to do this actually to death until you're super bored of it in the next video after this one. What do you think the angular frequency of a pendulum is going to depend on? So a pendulum is just, you take a cord and you put some mass on the end of the cord and you let it swing back and forth like that. That's a pendulum. So grandfather clocks have those. Most science centers have some random pendulum that's always knocking over dominoes somewhere. What's it going to depend on? What is the period, or what is the angular frequency of a pendulum going to depend on? If you make the pendulum longer, do you think it's going to take a longer amount of time or a shorter amount of time to go back and forth? How is the length of the pendulum going to affect the time that it takes to go back and forth? Think about that for a second. Okay. What about the mass at the end of the pendulum? Is that going to affect how quickly it goes back and forth? Its angular velocity, angular frequency? What about its initial velocity? What about this maximum angle? You know, there's got to be some maximum angle that it gets to. Is that going to affect how long it takes to go back and forth? What about just the gravity on Earth? Is that going to affect how long it takes to go back and forth? Think about this in terms of omega, the angular frequency. So remember, angular frequency was equal to 2 pi over the period, for example. Think about it in terms of the angular frequency. So how quickly it's going back and forth, that is the angular frequency right there. The amount of angle that it's going through like that per second is the angular frequency. That's a very important number. We plug it in right there. So what do you think the pendulum is going to depend on? Well, other people far smarter than me already figured that out. It turns out that the angular frequency of a pendulum is equal to the square root of the gravity of whatever planet you're on divided by the length of the pendulum. The longer the pendulum, the larger that number, so the smaller angular frequency. That means that a very long pendulum will take a longer time to go back and forth because it has a smaller angular frequency. It goes through less angle per second. And the more gravity you have, the quicker it should go back and forth. That kind of makes sense. If you're on a very low gravity planet, I'd expect a pendulum to go back and forth very slowly. So if g is a very small number, then you're going to get a very small angular frequency. So you're not going to be going through much angle per second as you go back and forth on the pendulum. Notice that it does not depend on the mass there, and it does not depend on the initial or maximum angle that you're at. Now that is actually only true when you are close to zero angle. When it's a very small angle motion, then the angle doesn't really matter, which kind of makes sense. If the angle is very small, it's not going to matter very much. But if you have a pendulum that's oscillating just 1 degree versus a pendulum that's oscillating 2 degrees, then they actually have almost the exact same angular frequency. Even though the 2 degree oscillation is twice as much as the 1 degree oscillation, the angular frequency will be virtually identical, which is an interesting result. Well, what can we do with this? Once we find G and L, we can plug it into any of our neat equations over here. If we know the amplitude, we know the initial angle or whatever, the phase angle, then we can generate these equations completely and track the position, velocity, and acceleration of the pendulum at any time in the future. And that's automatically pretty useful. What else can we do with that? Well, let's look at some examples. First example, Let's find the period for a 3.2 meter pendulum on Earth. Now, this is a good time for you to get your calculators and just plug things in. This is just purely plug and chug. So G, 9.8, L, 3.2. Divide those, take the square root. What do you get? Well, you get the square root of G over L. You get omega is 1.75 radians per second. And if you try to find the period from that, the amount of time that it actually takes to go back and forth, you get 3.59 seconds. Get some practice with that, just in case. Now, slightly more interesting, what if we took this pendulum, this 3.2 meter pendulum, what if we took it to the moon? Well, the 3.2 meter pendulum is now on the moon, if you can read my handwriting. The gravitational acceleration on the moon is 1.62 meters per second squared, and that gets us an omega of 0.712 radians per second and a period of 8.83 seconds. Good idea to just make sure that you can do these simple example problems on your own. Because I'm such a great artist, I drew this incredibly accurate diagram of what a leg looks like, and I overlaid a pendulum onto that leg. We can kind of think of legs being kind of like pendulums. I know it's not like really a pendulum, because a pendulum, all of the mass is concentrated at the mass at the end of the string. Your leg is not anything like that. The entire mass of your leg is not all in your foot, and if it is, you should go see a doctor. Usually you have mass all over your leg, and so this isn't quite accurate, but it is instructive, because we can actually find your most comfortable walking speed, or an approximation to your most comfortable walking speed based on your leg being like a pendulum. If you're walking comfortably, you'll notice that you're not really putting any energy into swinging your legs back and forth as you walk forward. You're not actually, exerting much muscle to make your legs go back and forth like that. Mostly you're just letting your legs swing back and forth naturally without having to think about it. Your legs are acting a lot like pendulums that don't have any extra energy going into them. If you interpret your legs like pendulums, you can find your comfortable walking speed. Well, any kind of speed, velocity, is going to be a distance over a time. The distance, in this case, is the length of a step, the length of your stride. So the length of your step is going to be, well, kind of proportional to how long your leg is, I guess. And then the t is the period of one step, how long it takes you to make 1, 2, 3 steps back and forth, like that. What can we do with that? Well, we start with our velocity of our walking is equal to d, the length of our step, over t, the period of a step. So if you have a very long step, then you're going to be going very fast. If the period of your step is very short, then you're stepping very quickly, and so the t will be very small, and v will be very large, and vice versa. Well, what is t? As I showed you on a previous piece of paper, t is 2 pi over omega. So I can do a little bit of algebra and get the omega up top. So now the velocity is going to be the length of your step times the frequency of your steps divided by 2 pi. Well, I don't really care about the exact number because none of this is going to be exactly exact. So I'm going to make this proportional instead, and I'm going to get rid of the 2 pi. Now, equal signs are equal signs, but this alpha, like that, that's actually a proportionality sign now. And so I know that we've used alpha as the angular velocity, but alpha can also mean something very similar to an equal sign. So just pretend that that's a very funny looking equal sign that gets rid of all the constants. 2 pi, those are constants. And so I'm not saying that velocity is equal to d times omega. I'm saying that the velocity is proportional to d times omega. Increasing d or increasing omega will increase the velocity. D is the length of a step, but the length of your step is also going to be proportional to the length of your leg. Someone with longer legs will take longer steps than someone with shorter legs will. So then I can say, well, if d is proportional to L, then I can just replace d with L and get that the velocity is going to be proportional to the length of your leg times the frequency of your steps. I can replace frequency with what we learned frequency is for a pendulum, the square root of g over L. Now I've got the velocity of your walk is proportional to the length of your leg times the square root of the gravitational acceleration divided by the length of your leg. And a little bit of algebra, you get that the velocity of your walk is proportional to the square root of the local gravity times the length of your leg. What can we do with this? I have a lot of friends that are a little bit shorter than me. If I was a foot taller than someone, that would also make me about 20% taller than that person, just, assuming 6 feet versus 5 feet kind of thing. And so if I'm 20% taller, that means that I have 20% longer legs. So if I have 20% longer for L, that means that my velocity is going to be 9% faster. This is why it's frustrating to take a walk with someone who isn't the exact same height that you are, generally, because a taller person and a shorter person will innately, because of physics, have different comfortable walking speeds. A taller person will comfortably walk faster than a shorter person. And it is just as uncomfortable for a taller person to walk slower as it is for a shorter person to walk faster. And yeah, that's annoying. But there's not much we can do about it because it's written into physics itself. Well, what about moving to Mars? On Mars, the gravitational acceleration is just 0.38 times the gravitational acceleration on Earth. And that means you plug in 0.38 in there instead of 1, and so you can compare the velocity on Earth compared to the velocity on Mars for comfortable walking speed. We see that we'll probably be walking slower on Mars. We'll only be walking 62% of our normal speed on Mars compared to Earth based on this. Everyone will have to be effectively power walking on Mars in order to be going just the same speed that we would be going on Earth.